I'm a minute late. Fire me. Okay, so let's just talk about linear programming just a tiny bit, and then we can talk about anything anybody wants to talk about. So I guess when I was first introduced to linear programming, I was already an assistant professor, and people were talking about it. And when you look at a linear program like this, minimizing a linear cost function with linear equality and linear inequality constraints, it doesn't look that interesting. Turns out there's lots of problems on graphs and things like that that people formulate that way, but it became much more interesting when it was explained to me that you could attack the one norm and the max norm using linear programs. So I thought we'd talk about that. So a lot of times when people are talking about stuff and you don't understand the vocabulary, then it seems very intimidating because they know so much more than you, okay? So they talk about LPs. We talked about QPs on Thursday, quadratic programs, okay? So it's minimizing. And that, an inner product type norm with linear constraints and linear inequality constraints. That was a quadratic program. This is a linear program, same type of constraints, and then a linear cost function. So how can you minimize something nonlinear like the one norm, which is a sum of absolute values, or the max norm, which is just taking a whole bunch of absolute values and then taking the max of them? It's extremely nonlinear. How can you do that with a linear cost function? Okay, so there's the MATLAB calls and stuff like that. So the magic is these things called slack variables. So these are extra variables that one introduces into the problem. So the number of slack variables is equal to the number of constraints here. So we're looking at the problem of minimizing AX minus B in the one norm. So we're experts at doing this in the two norm. That's our classic overdetermined problem. Okay? So how do you do that in the one norm? So here's the one norm, sum of the absolute values. Okay, so what we're doing is minimizing the error in the fits. So our notation towards the end of the class was we had y equals cx, and then we added a plus e on the other side to represent what do we have to put on the equation to represent that it's not really an equality there. And we'd minimize the unexplained part of the equation. So these slack variables are really AX minus B, the error term. So, if we had put an E here, it would look a little bit more like what we have been doing, because S1, S2, Sm is really the absolute value of the error S1 on the first row. S2 is the error in the second row. So this notation here just means AX, the ith row, is less than or equal to B on the ith row. Okay, so we want to find X that minimizes the sum of the absolute values in the error of the equation. And the way we get absolute value with inequality type constraints is we simply have AX minus B, and then we have minus AX minus B. Okay. So if S is an upper bounding AX minus B and minus AX minus B, then S is upper bounding the absolute value of AX minus B. And so now all we're going to do is minimize the sum of the components in S, and that will be minimizing the sum of AX minus B. So it's, it's, once you see somebody write it down very clearly, like it is here, and the notes where I took it are attached, it's clearly not me who did this, then it becomes fairly clear how you can solve this as a linear problem now. So S, to satisfy this, S has to be non-negative because it's AX minus B is less than or equal to S and minus AX minus B less than or equal to S. Okay, so that's, when you have that, then that tells you how you choose the cost function. So this 1 is just 1s in all of the entries, and so F times XS is just the sum of S1, S2, Sn, so it's the 1 norm of the vector S. And then the inequalities we're setting up are simply writing down the absolute value here, but doing it in a linear way by having the plus and the minus of each row here. And that's what these give you. And so you have the solution of this by solving a linear program. And these things are super fast. You can solve a linear program with 10,000 variables on your laptop in 1/10 of a second or less. Okay, they're super fast. Very, very large linear programs can be solved. Now the mistake that's on these notes is that, when you write argmin and an equals, this really should mean X hat is unique. And the 1 norm and the infinity norm, these are not strict norms. So you can have non-unique solutions. And so I'm just fixing that here. So if we're going to write X, it should be an element of, because there's a whole set of solutions in general when you have the, when you're minimizing the 1 norm. And when the algorithm runs, it will choose one of them. It's not going to give you the entire set typically. So it's possible to run it and it gives you a different answer each time, but it will give you an answer that does minimize the 1 norm. And so here, this is the example we had way back in September of when we were talking about uniqueness with the 2 norm, and that's kind of magic, that the 1 norm and the infinity norm don't satisfy that. So here's a minimum distance problem. Find x's such that you best approximate the vector 1, 1, and the x's lie in the subspace x1 plus x2 equals 0. Okay, so that's a subspace like this. And then you can check that all points x1, x2 satisfying x2 equals minus x1 and the absolute value of x1 is less than or equal to 1. Every single point satisfies that the 1 norm of that is 2, and that's the smallest value. And if you just go back to the posted lecture notes, all of the details of doing that calculation are given there, okay? So, not unique. That's what the main thing here. Okay, so it's a matter of cleverly changing the problem formulation, and the key thing is here you need the same number of slack variables as you have rows in the equation, so that when you write down x and minus it, you're able to do absolute value of this. Okay, so that's why there's M slack variables, where M is the number of constraints. Questions? Good to know. Okay, it's just one of those things that you would never think that you could just, hey, it's not a linear program. Yes, it is, if you're clever. So here's the other one that works with that. It's the max norm. Okay, so max norm. So it's just the worst case error. So if one of the errors, the smallest we can make the error in one of the components is 3, and all the others we could make 0, we don't care. All we're saying is we only care about the worst one. Okay? So the L infinity norm or the max norm, just the worst error. So it's the max over the absolute value of the errors line by line in the equation. Okay, so we're not worried about what's happening. We still have to have, okay, we're still looking at the error in the equation, and we're just looking at the worst case. So because of that, we only need one slack variable here. So that's the difference, because we only care about the worst case. We don't care about the other n minus 1s. We need one slack variable. Okay, because we're looking at ax minus b. We need every single row to be less than or equal to the absolute value of s, because we're just minimizing the worst case error. And so ax minus b and minus ax minus b, that gets us the absolute value part. Okay, so that's what this equation has, both of these in it. But because it's worst case, it's not S1, S2, dot, 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 SM. It's just S repeated on each row. And so this 1 is 1, 1, 1, 1, 1. So this is S, 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 the same S, the same S. And so if it's the worst case, then it has to be, this bound has to be satisfied for S. And so you minimize over S. And so F transpose times X will work out to be just S. And we choose S to satisfy this equation, which means S satisfies every single row of the equation. Its absolute value is less than or equal to S, and then that'll be the max norm of the error, the smallest S you can find that satisfies that. And so F trans X, you append one slack variable. F transpose, forget about X, you just minimize S. And then A and B and your inequalities is just writing down this equation, and it's negative. You get absolute value. And once again, the answer is not unique. So this should be element of, not equal to. And so let's suppose we're doing a minimum distance problem of the point 1, 1. We want to approximate it with an x hat that's in the subspace x2 equals 0. Well, this point would be fine. Okay, at least we'd have the x1 coordinate exactly equal to 1. And then the error is in the x2 coordinate, okay? But if we go over here, the maximum error is still in the x2 coordinate, and it's still 1, so that's still a solution. This is a solution. Everything over to here is a solution, and everything over to here is still a solution. So there's a whole interval of solutions where the error, the maximum error, still gives you 1. It's not unique. Infinity of solutions. So, okay, so if we were doing the 2 norm, we know it's orthogonal, but that's not true for the max norm and the one norm. Okay, all of these points are minimizers. All of these points have the same max distance to the point 1, 1. So there's no single best minimizer here. There's a whole family of them that give you the same solution. So, is that the norm you want to use? I don't know. That's up to you. Maybe you really do care about worst error, and maybe you don't. It's just up to you how you formulate the problem. Oh, I don't know the algorithm. I really don't know. Okay. So it will start and iterate, and I'm sure you can give it a warm start if you want. Okay, and it probably affects the final answer. But I haven't played a whole lot with L infinity, just because it's rare that I wouldn't want to do something to make the other terms kind of small if I can. So this one is super conservative as well, but the non-uniqueness makes it a little bit unsatisfying. But the problems are convex, and once again, as soon as you have it as a linear program, you can solve problems with 10,000 variables very easily on a laptop. I mean, a laptop. So. And then these are the source of my notes from Princeton. So, and I will note that he was super smart enough not to write argmin, okay? So I made that mistake, not my source. It was me. So, but it's sometimes good to make those mistakes and then to own up to them, and then maybe you won't make the same mistake just by accident, not thinking, just writing down argmin. But it's okay to do argmin if you put element of and recognize that this is a set. That's all that means there. Other questions? Yeah, so you could say this is the set of all arguments that minimize this. You could write it down as a set, and that could be quite nice, okay? Maybe you would like to have that set, and then you would add an additional constraint to choose a different element out of there if it was easy for you to get the entire set. Or you do, like is done here, and you just say, I'm seeking an X to minimize this scalar quantity. And you don't claim anything about uniqueness. You just say, I want a solution, and then it's all good. Then it's all good. So it's a linear program. And if someone said you could use this to do the one norm and the infinity norm, you'd go like, I don't think so, but in fact, it's true, okay? So, but it's the key thing is that you introduce these things called slack variables. And so the slack variables are the error in the equation ax minus b, for example, and that's what you do, okay? Okay, so what do you guys want to do for the rest of the time that you've paid for this object up here? I'm still being rented by your copious tuition payments, so how can I help? Please. Yeah. So the 2 norm, just because it tends, well, it leads to closed form solutions on many different types of problems. Also, it kind of corresponds to energy. So if you look at integral of the current squared when the voltage is constant. So that tends to be, if you look at you get resistance in the windings of a motor and you minimize the current. So then you're minimizing the induction winding losses and stuff like that. So the heating losses, people tend to do things like that. But it's just very, very convenient. So there's not as many algorithms that are fast and when you have minimized the 17th norm, for example. But this max norm, I mean, if you replace the infinity with p and you let p become large, then the solution does converge to the max norm. But if you put p here when p is 600,000, okay, so it's going to be really close to the max norm, but that norm is strict. So if you have between p strictly bigger than 1 and strictly less than infinity, then the p norm is strict. And so then you get uniqueness to these solutions. So you can do it, but I don't know of any really super duper algorithms for p equals pi or e or 17 or 600. So the 2 norm, speed, the 1 norm. So quadratic programs, people have worked on a lot, they're super fast. And then the linear programs people have worked on a lot, they're super fast. There may be reasons that the 3 norm doesn't have a fast algorithm. I don't know, I'm not enough of an expert to be able to say. Okay, others? Oh, yeah.
Stories about how that helps your research.
I'd be happy to. So I studied in my dissertation abstract nonsense. It's a high-paying field. No, okay. So I just did, I was a control student at the University of Texas at Austin, and they only had like 3 control classes when I was a student there. And then 1 course in estimation. So so I took all of my other courses in mathematics just because I had to do something and I enjoyed it. I hate crossword puzzles. I've never tried a Sudoku puzzle. Those type of things drive me crazy, but solving proofs of theorems and stuff, that always was fun for me. So that's what I did my dissertation on, was abstract stuff in that. And so then I worked in geometric nonlinear control theory with Alberto Isidori and Michel Fliess and Hector Sussman and those guys. And then I got to the point where I thought that stuff wasn't very fun anymore. It was just too completely abstract. And so I started working at Ford Motor Company in the summer as a faculty intern. So when I completed my PhD, I could not tune a PD controller, okay? I don't know, how good are you guys, okay? It's not easy, but I didn't have anything practical. So Ford was the first time that I started to be able to just look at problems, and then I would translate them into mathematics problems that I could solve. And so the first problem that they gave me that was super hard was they had a V6 engine. And so they were trying to do air-fuel ratio control, and they were just making the transition from carburetors to fuel injectors. So a carburetor, remember what that was? You have air coming in, and then you have this little needle valve that mixes air, and so the air and the fuel gets mixed in the intake manifold before it goes into the cylinders, okay? So they're just starting to make this transition, and so what they were doing is kind of putting a single fuel injector in the intake manifold instead of putting 6 of them in the cylinders. Why? Cheaper. Hey, this car is $300 cheaper than this one, and they're all the same. More people will buy the one that's $300 cheaper, okay? The problem they were having is that the engine would not idle smoothly because you would get imbalance on the two things. And so I formulated it as I recognized that this was a periodic control system, that I could lift it up in a certain way, and then I reduced everything down to a root locus problem that the engineers could understand. But the theorem underneath that was really flow-K multipliers and abstract nonsense like that, okay? So I told them you go in, and if they move the gain this way, this is what's going to happen, and they move the gain this way, that's what's going to happen. They didn't believe it, but they went in, they moved the gains that way. It's exactly what happened. They said, oh, this guy knows what he's talking about, okay? So then the next problem they gave me is they now had made the transition on this other car to nice fuel injectors and everything. But you have this thing called an exhaust gas oxygen sensor in the exhaust manifold. So it measures the ratio of essentially estimating the oxygen content and its ratio with the hydrocarbons. And so if that ratio is 14.64, which is stoichiometry for most gasolines, then the catalytic converter could have conversion efficiencies up in the high 90s, 97, 98% of the nitrous oxides, the carbon dioxides, and the carbon monoxides would be completely eliminated. And you would have, this carbon monoxides, the nitrous oxides, and then they would all be converted into CO2, which is not great, but if you're burning fuel, you can't remove CO2, but you get rid of all the nitrous oxides, you turn it into N2, so nitrogen is coming out, and then oxygen, okay? So 98%, not too bad, and then only 2% of the other stuff would go through. So to do this, though, they only wanted to have one exhaust gas oxygen sensor in each of the banks of the engine. Why? Cheaper, but also reliability. If the exhaust gas oxygen sensor fails on a car, you have to turn on the idiot light, and you have to make it so annoying that the person will take the car into the dealer and get it fixed, because the conversion efficiency of the catalytic converter will drop down to about 20%. And so your pollution just goes way out the window. So the question was, if we could make the fuel ratios balanced in all of the individual cylinders with only a single sensor in the exhaust. Okay? And so some physicists came up with this scheme that they were going to do it, and I got their data, I analyzed it with the singular value decomposition, and I told my boss when I walked out at the end of that summer that this is never going to work, it's too sensitive to this and this, and that if you want, we can work on that next summer if you will have me back. So I did go back, and they said, yes, it had all the problems you said it was going to have because I analyzed all of the data. And so then I went and once again formulated the problem as a control system. And once again, linear, time-varying periodic systems, and I knew how to lift them with flow-K maps to these time invariant systems, and I could check the observability and controllability of the systems when I did that. And I could check that on this 4-cylinder engine, everything was fine. And so I designed a PI controller, a really simple PI controller, and I said, this will do it. And they said, fine, implement it. And I went, holy shit, excuse me, the camera's running. I didn't say, I said, holy S. Anyway, don't report me, please, okay? Just telling stories. So I had to go off and learn C++. I didn't know, I was trained in Fortran. I had learned how to do the machine language that they used at Ford because when they were writing my algorithms before, they were making mistakes and they would blame and my math was wrong when it was just the coding. So I learned how to do the machine language coding, which I was taught as a grad student how to do machine language for PDP-11s, okay? That's how old I am, okay? It was part of an electrical and computer engineering degree to learn how to do machine language coding of PDP-11s back in the day, okay? So I knew Fortran, I knew that, I didn't know C, so I went off and learned enough C to program everything up in that so that my part of that would work. We put it in the engine, and the engine goes, boom. That wasn't good, okay? So it turned out I had the most important number in a control system wrong. The most important number in a control system is when you have this thing and this has a minus sign and this has a plus sign. So the technician and I misunderstood each other on the direction that this one thing was done. So fortunately, I knew what to look for, and 3 minutes later, the thing is humming, and then all these air-fuel ratios were like this, and they start going like this, and then all of a sudden, they're just all constant, and they're all equal to stoichiometry, and everybody's going like, how did that happen, okay? So then somebody went out, running out into the hallway, yelling, "The egghead has it working. The egghead has it working." You cannot make this up, okay? The egghead has it working. So that established model-based control as the way to do all of the emissions and fuel economy analysis at Ford, and now it's a really big field in academics. Before that, people were still just, tweaking and everything, not doing models. So that still hasn't gotten me to robotics. You guys bored? You want me to stop or just keep going? Okay, so between the automotive stuff and robotics, I did some semiconductor manufacturing work on reactive ion etching. That was fun. It was a big group project. First time I'd worked with 15 of us all working on something with our students. That was really cool. But then I'm a full professor and I've got a sabbatical. So sabbaticals are these periods where you can go off and learn new things. So I had one semester, and my girlfriend at the time, who's now my wife, okay, she had a sabbatical at exactly the same time, and she wanted to go to France. For me, that was easy. I had done my postdoc in France, so my French was good, and I'd been back a couple of other times. I've given lots of lectures in French, so I said, fine, any place in France you want to go, I will know somebody, and I will get myself invited. So she had a position at a really prestigious biological and microbiology institute in Strasbourg, France. It's right on the border with Germany. At this time, the borders weren't open. You still had to show your passport if you went across the borders in Europe. The Schengen stuff had not happened. Okay, so we're right there in Strasbourg, and so I got myself invited to a physics institute there. And that's where they were building this rabbit robot. So rabbit is that small silver robot that maybe you haven't had a chance to see. I can show you videos if you want. But they had a team to design the robot, but nobody to do feedback control. So they had a really, really good person who knew how to do optimization of gates and stuff, but nobody to do feedback control. So I said, okay, that sounds fun. So I took on the problem of doing gate design for rabbit. And it took me a little while. I tried many of the techniques that Professor Spong talked about here 2 weeks ago in the control seminar. And let me tell you, they don't work, okay, on real robots that have harmonic drives, because the relationship between the power you're commanding to the motor and what's going to the joint, there's almost no relation because of the inefficiencies of harmonic drives, and Rabbit had harmonic drives. So I tried all of that stuff until I figured out that that stuff was just not going to work. And then I hit upon this work that I had done way back when I was doing abstract nonsense called zero dynamics. It was invented by Alberto Isidori, Chris Burns, and Claude Moog, one of my buddies, played a small little piece of that. So zero dynamics is the following. You have a nonlinear system, x dot equals, and you have an output y equals h of x. If you clamp y to 0 and look for the the largest dynamics inside that's compatible with the output being 0. That's the zero dynamics. So maybe it's only the equilibrium point, maybe it's something bigger. But the magic thing about a zero dynamics is if that's exponentially stable and you know how to drive the output to 0, then the overall system is exponentially stable. So in the nonlinear area, that was used for analyzing stability of equilibrium points. But these robot models, they're all hybrid, because you have the Lagrangian dynamics, and then you have an impact. And when you have an impact, the velocities jump. And so none of the theory worked for that. And I didn't want to do analysis, I wanted to do feedback design. So I took those techniques and I turned them into a method to do gate design. And it was really nice because I could prove hard theorems about the stability properties of these gates. And for a certain class of models, I could do essentially closed form analysis of the stability of the orbit and give you a simple stability criterion. And so, even my colleague, Christine Cheval-Leroux, with whom I've done so many papers since then, when I told her about this, she just goes, yeah, right, okay, So it took me a long time to convince people in the robotics field that this would be something that we could do. I had lots of people tell me it's not going to work. It's nice theoretically when they finally accept it, but it's never going to work on a machine, etc. But we got it to work on Rabbit, and then we got Mabel. And we're using those techniques. She could run at a 9-minute mile, and then we did Marlowe, Cassie, all these other robots. So now it's kind of recognized as maybe the major way to get dynamic motion in bipeds. But if I didn't know all the abstract nonsense, I would never have been able to take this analytical tool from nonlinear systems and turn it into a design tool for robots. And that was the thing. The nonlinear control people, they never thought of taking it and inverting the problem. How do I design the output to make the internal dynamics compatible with the output being 0, have desired properties? So I think this is where the math skills come in, is that the ability to take things that no one's ever done and just understand why they work and then try to be able to use those tools in new and very creative ways. So that's one set of stories. Another set. You guys bored yet? You want me to stop? Keep going? You want some pictures with the next one? Yeah? Okay, let's see if I can get my laptop going again. Where'd you go? Yeah, I'll go a little bit quicker here. Yeah, anybody wants to leave, that's fine. I'm not, I don't care. Okay, so here's these robot models, why they're hybrid. You have when one foot's on the ground and not moving, it's just the standard robot equations. But when this foot, the swing foot, comes forward and hits, it decelerates very, very quickly. So you have two choices here. One, you can take the impact time. So in our lab, with the robots that we've had in there, it takes about between 20 and 30 milliseconds for the foot to come to rest. Wow, you know, how much time do you want to spend modeling something that's that short, okay? So if you could then just take that limit and make it 0, and then the force becomes an impulse. Now, if you take a second order a linear dynamical system, like a double integrator or something, and you just put an impulse into it, what happens is you get a jump in the velocity and the position stays constant. So just go home and check it with your Laplace. So you can do the same thing with these nonlinear robot equations. The other thing is you can model the impact as a spring damper. So that's more accurate. But then what is the spring coefficient and what is the damping coefficient? I don't know. Is it the same for this as it is for the carpet? The answer is no, okay? So which one do you use? Well, depends where you are, but I want to go lots of different places. So usually what it turns out best to do is to just forget about the spring damper because you can't figure out the right model parameters and to use this thing, okay? So this is just showing the model equation. So here we go. So there we do the models. You get this hybrid system, meaning it's Lagrange. You have an impact. You get a new initial condition, it evolves till the swing leg comes forward. So that's the hybrid stuff. But here's the problem. Even for Rabbit, okay, Rabbit, is you up there? There we go, there's Rabbit. So Rabbit's this planar 5-link biped, motors at the knees, motors at the hip. It's 1, 2, 3, 4, 5, 6, 7 pages of 10-point font for this robot. For Cassie, it's something like 1,000 pages, okay? So this one, I derived the Lagrangian and et cetera, and my students checked it. So this one we did by hand, and so we know every line in there. We did everything. But Cassie, no one's ever looked at every line of code in the model, okay? So let me jump to this new way of doing feedback design. Okay, so you guys are going to be taking courses in like supervised machine learning and stuff here pretty soon. So you've heard the word neural networks. Yeah, it's kind of like black magic. I mean, it's really regression on steroids. It's very, 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 very complicated functions that are supposedly modeled on neurons. Who really believes that? Okay. And then it's a regression problem, just like we've solved the linear regression problem, but it's a nonlinear regression because you're fitting a nonlinear function to data. So one of my students, I'll get to him in a second, was starting to use neural networks in the control. And my lab, one of the big things we've been proud of is we have firm analytical theorems, okay? And he's using neural networks. I'm going, la, 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 la. You know, every time you tell me about it, I just kind of ignore it. Until he had it working on the robot and it was killing everything else that we were doing, okay? So then I had to go, holy smokes, what's going on here? So 2 years ago, Dennis was still here, Da Xingye, he goes by Dennis. So I sat him down in the office and we met for an hour a day for a little over 2 months. It was really frustrating for him, because it took me a long time to understand, and super frustrating for me, because a lot of the stuff, he didn't have the mathematical training to write things down in the right way. But finally, after 2 months, literally, of meeting an hour a day, sometimes more, for 5, sometimes 6 days a week, he writes down this magic equation, I call it, because from that one equation, it was the little thread that you pull that takes this huge knotted math problem and just untangled it completely, okay? It was beautiful. And there was a theorem underlying what he did. And so that's what I can tell you about. So Ayunga, he's going to be a faculty member at Ohio State starting in January. So he's a postdoc in the lab. When he was at Georgia Tech, as a PhD student, he took some of these optimization problems that we solved for gates that were taking hours, he turned it into minutes. So for Rabbit, Rabbit was 18, 19 years ago using MATLAB. We could solve periodic orbits in a couple minutes. With Mabel, she had these great big springs, and they're stiff, but you needed to use them because Mabel was a pogo stick. I mean, it was really, really interesting robot. That would take a couple of hours. Our robot just prior to Cassie was Marlowe. She'd be outside on the wave field and stuff, so the robust control designs on her were taking overnight. And Cassie would have been a week or more, okay, to calculate a single gate. And so he turned that into minutes. We're going like, whoa. So that was a game changer. And so it was fast, but not fast enough to do model predictive control. You've heard about that maybe. So with model predictive control, you say, I'm not going to compute my controller offline. I'm just going to do it online, and I'm going to do the following optimization. I've got my model, and then I will minimize some cost criterion subject to constraints, and my cost criterion will be planning outwards, say, 10 seconds ahead of where I am, or maybe a minute or something like that. So it's finite horizon, etc. But the problem was, each step on our robot is less than 1 second. And if it's taking a minute to solve one of these optimization problems even, and Ayunga's was 4 to 5 minutes, you still can't do it in real time, what he was doing. Okay. And then what people were also doing is said, well, if you can't solve it in real time, do those calculations offline and then store it in a grid. And that's called explicit MPC, where you solve a whole bunch of things and then you just do table lookup online, okay? You just store it as a table. You get a value here, one here, you're here. You just do kind of a linear interpolation, okay? But the problem is you can't do it. Suppose you only put 5 points per dimension, and this number, well, with 20 degrees of freedom, that would be 40. I don't know what 5 to the 40 is. You can check. It's bigger than all this number of stars in the entire universe, okay? But when n is 16 for Marlowe, it's something like 15 billion optimizations you would have to do. So explicit MPC, that's not going to work. So Dennis here, who's now at NVIDIA, earning more than I do, okay? He started in April of this year. He invented this whole new technique, and then now everybody in my lab wants to do that, okay? So this would just have stayed as sort of, yay, we're just like everybody else, we're doing neural nets and stuff, but because of, once again, how math helps you, talking to Dennis over and over, where I would just teach him more math, And then he would write down equations, and we'd figure out, no, that's not the right way to do it. And I'd teach him some more math, et cetera. And then finally, with the math I taught him, he writes down this magic formula. And so he's able to do the following. So due to a Younger, we can calculate trajectories for the robot very fast, okay? So minutes for each of these, and you could do this in parallel, so you could do many of them in several minutes. The problem with a trajectory is if you get pushed off it, what are you supposed to do? Should you steer yourself back to the trajectory that you were following? Well, no. What you would really like to have is that there is, say, this is a periodic motion, and with the hybrid map, it comes back around. If you're following this and you get pushed off, get on the next path that's taking you forward. So a vector field in the language of computer science is an instantaneous replanner. So it's just a differential equation. So you guys know that the derivative is supposed to be the slope of the trajectories, right? That's the little arrows, okay? So what he really did was he took a behavior, a collection of trajectories, and he built a state variable realization of them. So he built a differential equation living on that surface such that solutions of this differential equation would be the original trajectories in the model. And then we would use the techniques I had developed a long time ago to take points that were off of this trajectory and guide them, the surface, and guide them back down. And so this is where he did it, and this is where the machine learning came in. It's taking these trajectories and turning them into a vector field. So there's a theorem around that. So to turn it into math, you first need to understand what steady state walking is, okay? How to find periodic solutions and how to check stabilities. And when I show this to you, you're gonna go, oh, that looks like a contraction mapping, okay? So this is called a Poncare Map. Just like we were using P for the contraction mapping, like most people do, they use P for Poncare here. So here's a Poncare map. So this is, if you have a guess that there's a periodic solution, what you do is you take a hypersurface, so one dimension less than the ambient space, and you put it, it doesn't have to be normal. We don't have any notion of an inner product in here, but it just can't be parallel. We know what parallel is because we know what a derivative is. So it has to be transverse, meaning not parallel. Okay, so that'll mean that if I start on this surface and I come back around, I'm going to have intersections because, you know, in 3 space, I've got to go through a 2 space. And so we do event-based sampling. And so the Poncare map does this. You start out with your initial condition. There's my jump from the impacts. I now follow Lagrange's equation and my feedback, and I come back around. And so that's xk, and that's xk plus 1. So guess what? If I start at a point and I come back around, that's an equilibrium motion for my robot, but it's a fixed point for this mapping. So now you know a physical fixed point, okay? An equilibrium point of a Poncare map. Now, under what conditions, if I perturb off and I go around a couple of times, will I keep getting closer and closer here? So you guys, if you took the linear systems course, you did differential equations. You can do difference equations. And the condition is if I linearize this map, so there's the Jacobian, and you guys know how to calculate numerically these Jacobians. If the eigenvalues are inside the unit circle, then you get local exponential stability. Okay. Well, that's hard to check because to calculate all these Jacobians, remember this model is maybe 40-dimensional. And so that's hard to check. So here's another way to do it. I give myself some delta positive. I give myself some c less than 1. You guys have seen this parameter called c less than 1, okay? And I make sure that each time I go around, I'm getting closer to my equilibrium point. So I'm turning this, what I want to do is build a contraction mapping. So I'm building a contraction mapping, okay? And I can just use any norm I want. So, you know, for lack of a better one, we typically use the 2 norm. We could have used the 17 norm just to be interesting because I'm going to use this as a condition to get local exponential stability. And this is very easy to check on trajectories. And what I have that I can calculate for almost free thanks to a Younga are trajectories. So anyway, by the way, when I was doing and talking about doing abstract nonsense, I knew how to do manifolds and vector fields and Lie brackets and Lie groups and all this stuff, but never applied on anything real, okay? Just doing mental puzzles. So this working in robotics allowed me to bring back my abstract nonsense and apply it to something physical and turn it in from analysis into design tools. So I'm going to take this analytical condition that gives me Cauchy sequences and everything and turn it into a feedback design method. Okay, so I'm going to forget about the hybrid stuff for now. And we're going to assume that we've designed a periodic solution of the robot equations. So I'm going to have an initial condition. It'll have a period, say 800 milliseconds or something. Now I'm going to design a whole bunch of other trajectories. Okay. So this is just notation. I don't know, it seems simple notation to me, but it's driving crazy the reviewers. This is just meaning a solution of my differential equation, and that's the initial condition, and this is the time between 0 to TP, okay? So phi sub zeta is just a solution corresponding to whatever initial condition I have. And so zeta star is for the fixed point. Okay, now I'm going to do an open ball. You guys know what open balls are. You know about contractions. Okay, I'm going to design a whole bunch of other trajectories. So I have inputs into my system. I have resulting state variable solutions. These are just points in my open ball about my desired periodic orbit. And my differential equations are going to start at my given initial condition. They're going to terminate in my open ball, and they're always going to get me closer to the equilibrium. So I'm building in stability. Okay? So this is an easy boundary condition on an optimization problem. These are easy boundary conditions and optimization problems. Okay? So they're defined on the same time interval. They start in the open set. They end in the same open set. Why is that important? If it ends here, then I can just sample that point again and calculate another one of these things and come back around, and I'll be even closer. So I can just keep spiraling. It gives me the fact that I have infinite executions in the CS language, okay? And then I keep getting closer to my equilibrium point. So I'm just developing that. And so we used to use a Younga's results, and we set things up as an optimization problem, where this is usually quadratic in the torques with some small penalties perhaps on the state variables. This is just a fancy way of writing down a differential equation in terms of an integral equation. And then we put a whole bunch of constraints, and the constraints are my torques can only be so big. It's a robot. The motors have finite size and finite power, finite torques. The ground reaction forces that we talked about a little bit on Thursday, I need those to be in a friction cone. Some of my joints, I can't have my legs crossing. They'll bang into each other. I can only bend the knee joints on Cassie so much. Marlowe, they had limits on how big the joints. So this is where a lot of the physical constraints go, and this is just kind of the differential equation, and this is minimizing energy in the control signal. Okay, so cost, solution, constraints, invariance, boom. And so we get, everything goes well, they go like this. Now, this doesn't make any sense until I put up this diagram. I want to do differential equations. If my trajectories cross, you know, the nice thing of, if a differential equation has any kind of smoothness, like Lipschitz continuity or something, you get unique solutions to your differential equations. This is not a unique solution, okay? I start at this point, I could go this way or I could go this way. It would depend upon the past history, okay? So you can't always get this nice picture. There are geometric impediments to it. So you don't want that picture. And so it takes some mathematical skill, some luck in how you set up your constraints, is what I'm saying here, okay? And the luck part means we still haven't figured out everything perfectly, okay? Being very straightforward. Okay. But anyway, this is all leading to neural nets, but there's a method to the madness of what Dennis was doing. So I'm going to show you two feedbacks, and then we'll kind of we'll stop there, okay? So here's one feedback. You know, I've got my surface and my ball, I've got my point, I calculate a solution such that my trajectory is converging towards my desired periodic orbit, okay? So every time the state crosses this surface, I grab that value, and then I use the corresponding control. So I cross the surface, I freeze the state, and then I go open loop. That evolves, it comes back around, I re-update the state, and then I go open loop. It's a fancy way of doing digital control. So it's really a zero order hold. Okay, and so here's how this feedback works. I grab the state value, I look up the corresponding control. It evolves, okay? This gives me a new state value. I look up the corresponding control and I apply it over the period. And then I keep doing that. Bingo, okay? Does this give me a stable closed loop system? I don't know. Let's calculate the Poncare Map. Okay, so here's my surface. My surface is just I'm going to add time to my states, and every TP seconds, I just grab the values. So I'm just setting up a Poncare analysis. I'll be quick here. You guys know what the Poncare maps are. But this is the boundary condition I was using when I designed my orbits. So it means my Poncare map is contracting. And you guys know that that gives you exponential stability, okay? So I create Cauchy sequences. I'm in a finite dimensional space. They have limits, okay? So the boundary condition that I put on my optimization problem guarantees this. Now, I never really compute this map. I simply evaluate this condition, and then it guarantees that this map exists and has that. I never have to compute that. So it's just there. I get stability from that. Okay, so this system is going to be exponentially stable, but it's a horrible controller. Okay? And then I'm going to give you the good controller that Dennis designed. Okay, so this is a controller. So I'm going to take the inverted pendulum. What is used, the period is 2 seconds. It does not have a fundamental period. It's time invariant. So we'll just use 2 seconds. We design this first feedback. We start away from the equilibrium. Here's the control. Here's all the states. It takes, I don't know, 5 seconds, and I'm really close to the equilibrium. So that looks beautiful. But now, I apply a perturbation half a second before I make the next state sample. Okay? Half a second. And then, boom. Okay? It's a terrible controller because it's open loop in between the state samples. It doesn't work in practice. Okay, but when the control updates, it removes the perturbation as long as the disturbance went away. So it does work. So let's get a second feedback, and then you'll understand the magic formula that Dennis wrote down that allowed all this other math that he and I were doing to fit together. Okay, so remember, these are the trajectories that we computed starting in this ball. We're going to do the classic Gerdunken thought experiment, okay? So I'm going along, and I'm pushed off my trajectory. What control signal would you like to apply at that point? Yeah, so if you can figure out this trajectory, then at this time you want to apply the control signal that would be with this, because this point you know is getting closer. Okay? Yep, so that's the one you want. So how do you find it though? All you have is a book listing of feedback signals and state signals. Well, here's the magic formula, okay? It's an interpolation condition. The controller that I apply at this time TD at this point in my state space is equal to the control signal that corresponds to here, okay? Now, this is written down. I don't know this because I'm here. I would have to flow backwards and read this and then go forwards. That looks really impossible to pull out of data, but it's not, okay? So there's the magic formula that Dennis wrote down for me. This is way too smart for me, okay? It's an implicit equation, and this is what he was solving with his supervised machine learning. And let me show you how. So we have all of these trajectories, and we have all of the corresponding open loop feedback controllers. Why don't we have a closed loop controller? We don't know how to compute one. What do we have? A tool that computes trajectories super fast. So can we take that tool and turn it into a really good feedback controller? So this is what Dennis does. He says we can sample the state trajectory at different times. And so we're going to build up a mapping, yeah, from features to labels. Okay? That's the vocabulary in machine learning, okay? It hurts me to use it because it's just a function fitting problem, but it's a really good tool. Then I take another state variable, my trajectories, and I sample it. And I put that in my table. And then I do it again. Okay? So if Dennis's interpolation condition holds true, I can now find a function that gives me these values as a function of time and state. And that's a state variable feedback, time varying. Okay, so once again, a word that it's hard for me to say, we learn a policy. Look, we're just fitting a function, okay? Not learning anything, except we're learning about machine learning. But they like to say we learn the function, okay? Just regression, we're fitting the function to data. And so, you know, it'll look something like this. And then we use the tools in MATLAB to check that we're not overfitting, okay? So we only use, say, 60% of this data. We build the function, and then we check the fit against the other 40% that we didn't use in it to make sure that, you know, they're not sitting way up here. Okay. Okay. But then there's a theorem that says if I have an open loop system that satisfies conditions that robots do, and I can find a time varying feedback that is, this is my period for my gate. Here's Dennis's interpolation condition. Then, and we design these things such that we have this contraction property that I mentioned, then the origin of this closed loop system is exponentially stable. And so that's the main theorem, the learning condition, the vector field. And then you put this on the inverted pendulum on a cart. Remember, that's the old one. And here's the new one, because it responds immediately to the disturbance. I mean, it just takes it out. It's fantastic. Now, the next problem Dennis had to solve, though, was that if you do this on Marlowe and you only put 5 samples in each dimension, 5 to the 16 is 152 billion. Okay? Dennis did it with 25, okay? That takes more math, and I'll let you read his paper that's up on the archive and on my paper, on my website. So his work is absolutely brilliant, and my role was not letting it just say, this is what we're doing with neural networks, and just teaching him enough math that we can write everything down with solid theorems and saying, we only need the machine learning to extract out functions from data, and this is how we're doing it. Okay. 25 trajectories, he'll build a controller, yeah. Yeah, and that's the one that worked on the wave field, okay? Yeah. That's why he's making more money than I am at NVIDIA, okay? So, the paper still hasn't been accepted in IJRR. The math is a little too hard for most people in robotics, it seems. I think we would be considered straightforward for every one of you in math, in robotics 501 to read through the paper, okay? I think every single one of you could read through the paper and understand what's going on. Only thing you'd have to look up is what is the definition of Lipschitz continuity, okay? So, yeah, yeah. And it's with Dennis, so, and it's an International Journal of Robotics Research. Okay, so we'll stop here. Kind of a leading question. Can you tell stories about math? So that took us from grad school days to not being able to tune a PID controller, being afraid of examples, to working at Ford, and then just taking problems and using the mathematics to formulate them in ways that were not common at the time, and then keep doing that in no matter what we're doing. And so another kind of math story just to wrap up. So the Kalman filter, you can do that on nonlinear systems as well as an approximate filter. And so a theorem that my very first PhD student proved with me was, if you do that on a nonlinear system and there's no noise, is this provably a stable estimator? And so nobody had done that. That was kind of surprising. The Kalman filter was invented by Bryce and Kalman in '58. And we're working on this in, I don't know, around 90, okay? So it's been a while. And we proved this theorem and blah, blah, blah. And then I did nothing on Kalman filters for the next 25, 28 years. But my current senior PhD student, Ross Hartley, found a really nice math paper in France showing how to do Kalman filtering properly on matrix Lie groups. So Mani, anybody here in Rob 550 who attended Mani's talk 2 weeks ago? A couple of you did. So he explained a tiny bit about this extended Kalman filter. So there's a way of doing filtering on Lie groups, which is once again more abstract nonsense, but they show up in robots. And if you do exploit the properties of these robot equations, then you get super, super stable estimators on nonlinear systems, which is uncommon, okay? So all I can say that it is very uncommon, but once again, having these mathematical perspectives can help give you a leg up on everybody else in the field. It was considered how to run these Kalman filters on robots and everything. Everybody's been doing the same thing for the past 30 years, and now it's changed, okay? So it's fun. The math does it. Anyway, that's it. Thanks, guys. So we'll have the review sessions Saturday, or Q&A session Saturday and Sunday. And the exam coming up.